Okay, good morning, everybody. I'm coming to you live from my kitchen. I actually did a lot of this work myself. In another life, I would have loved to have been a contractor. But that's not what we're talking about today. We're talking about the second law of thermodynamics. So in a previous video, I ended with this result. So it has to do with when changes occur. And specifically, we found that when a system is at equilibrium, delta S total was equal to 0. And when the delta S total was greater than 0, a spontaneous change occurs. And I suspect that some of you might have scratched your head a little bit and asked this question, right? This is not really what I learned in Gen Chem. In Gen Chem, I learned that delta G equals 0, means the system is at equilibrium. So what's going on? And that's what I want to talk about today. We're going to talk about free energies. It's in Atkins 3D, specifically the Gibbs energy and the Helmholtz energy. So away we go. My animations didn't work, but bear with me. This is the second law of thermodynamics. Delta S total is equal to delta S of the system plus delta S of the surroundings, and I know that it is greater than or equal to 0. Again, when the system's at equilibrium, it's equal. When the inequality is in place, a spontaneous change occurs. We talked a little bit about delta S of the surroundings, and I tried to make this argument to you. The heat lost by the system was gained by the surroundings. So Q reversible of the system is negative Q of the system. I think I said that backwards. Q reversible of the surroundings is negative Q of the system. And this works regardless of the path, right? So I can take this definition and I can substitute it into this expression for delta S of the surroundings. I get something that looks like this. I take and multiply both sides of this by negative T, and I end up with this important line. Q of the system minus T delta S of the system is less than or equal to 0. It switched to less than because I multiplied by a negative T. This is a statement of the second law of thermodynamics, right? It started here and we ended here. We just did algebra. So this is a way to state the second law of thermodynamics. And what we do at this point is we consider two different scenarios to describe the heat, which is released or absorbed from the system. The first is a constant pressure scenario. If I have a constant pressure, Q is equal to QP, and that is equal to delta H. So I can substitute this in, and I get an expression like this. Delta H of the system minus T delta S of the system is less than or equal to 0. The complement to that is constant volume. QV is equal to delta U. I substitute that in, and I get delta U minus T delta S of the system. And I've done a really tricky thing at this point. Right? Again, I started here at the second law of thermodynamics. We just did algebra. We end up with these equivalent statements of the second law of thermodynamics, but now they are written entirely in terms of changes in the system. Right? And so Atkins actually calls this section of his text focusing on the system. Right? These two definitions, delta H minus T delta S and delta U minus T delta S, suggest that we define two new thermodynamic variables. So those thermodynamic variables are described here. The first is the Gibbs free energy. G is equal to H minus TS. Or if I have constant temperature, we often say delta G equals delta H minus T delta S. The second is the Helmholtz energy, This one you probably haven't seen before. It's given the symbol A. A is equal to U minus TS, or delta A equals delta U minus T delta S at constant temperature. Free energies have two important uses. The first is that they define the criteria for spontaneous change. In other words, they'll tell me if a system is at equilibrium or if something's going to happen. The second is that the change in free energy represents the maximum work a system can do. That's where this free part of the name comes from. So it's energy that's free to do work. And I want to talk about these two things briefly. So the first point, and this is the most important one, is that free energies define the criteria for spontaneity. I'm not going to belabor this point because I think that you understand this pretty well from general chemistry. But here's the idea. If I made some plot of the Gibbs energy versus time, what will happen is that this will decrease, decrease, decrease. I can get my pen to work, it will decrease, 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 and then eventually it will bottom out. Right? Up in this region, if delta G is less than 0, if it decreases, right, a spontaneous change occurs. Stop, don't do that. The second is here, and in this spot, delta G is equal to 0, which means the system is at equilibrium. I hope this is familiar to you from Gen Chem, right? Delta G less than 0, the forward reaction occurs. Delta G greater than 0, the reverse reaction occurs. Delta G equals 0, it's at equilibrium. This is the first and most important use of free energies. There's one important difference that we need to recognize in PChem. So this is our definition of delta G. Delta G equals delta H minus T delta S. If I have increases in entropy, that will favor the forward reaction, or if I have a decrease in energy, that will favor the forward reaction. And so one question that we often ask students in general chemistry is, what drives the reaction? The increase in entropy or the decrease in energy? And we actually frame this in a slightly different way in PChem. What we ask instead is, what drives the reaction? The increase in entropy of the system or of the surroundings? Remember, the starting point for all of this was the second law of thermodynamics, which concerns the total entropy of the universe. This is a clever way to get around dealing with the surroundings. And this term here, has to do with delta S of the system. So if delta S of the system is positive, that's clearly going to favor the forward reaction. This term here, the delta H, is related to delta S of the surroundings. Remember that heat released by the system is gained by the surroundings, so that's an entropy increase of the surroundings. And so you'll see questions like this on the homework and other places. Here's the second use of free energies. They define the maximum work that a system can do. So bear with me. I'm going to do one derivation for you. And rather than working with the Gibbs energy, I'm going to work with the Helmholtz energy. So I'm going to start here. A equals U minus TS. And what I'm going to do is take a general derivative of this expression. I'm going to differentiate it. And that's going to leave me with this. dA equals du minus, this is a product. So I have to use the product rule. So that's TdS minus SdT. Derivative of the first, leave the second constant. Derivative of the second, leave the first constant. And I'm going to take, and I'm going to write this now in terms of the second law of thermodynamics. I know that this is less than or equal to 0. Right? That's what the second law of thermodynamics tells me. I'm going to do some rearranging. Right? So I'm going to bring the dA over here. This will switch signs. dA is greater than. In place of U, I'm now going to use the first law of thermodynamics, which tells me that this is dQ plus dW minus TdS minus SdT. What I want to do here is deal with dQ. And I might remember that ds is dQ reversible over T. So if I solve this for dQ and I plug it in, I get something which looks like this. dA is greater than TdS plus dW minus TdS minus SdT. Cancel, cancel. I have dW into minus SdT. I'd like to get rid of this term. So I place a condition on this, which is constant temperature. And if that's true, I get something which looks like this. dA is greater than dW. Well, I was really close, but I just overlapped a little bit. Here's what this means. The change in Helmholtz energy is greater than or equal to the work. Right? In other words, this change in Helmholtz energy is equal to the maximum work that a system can do. It's a maximum if the change occurs reversibly while the system's in equilibrium. It's an inequality if it occurs spontaneously. Some of you may be confused by the inequality here. Looks like this is bigger than the work. But remember that work is negative. When the system does work, it's a negative quantity. So we're saying here that it's less negative, it's bigger. We actually don't use the Helmholtz energy all that often in chemistry. Every once in a while, but not that often. More frequently, we use delta G. And it will turn out that delta G is greater than or equal to the maximum non-PV work. So the change in Gibbs energy is equal to the maximum non-expansion work that a system can do. And some quick examples of non-expansion work that are relevant in chemistry are things like electrochemistry. So you might remember using delta G's to calculate cell potentials, electrochemical cell potentials or something like that. That's where this comes from. Surface tension with bubbles is another example. So this is the second use of free energies, right? They tell us the maximum work that a system can do. I have some problems for you to explore this a bit. Look at them, they're good. There's some interesting kind of curious effects. And I will see you next time for a discussion of Maxwell relationships.